So this is currently being recorded. Okay, we are going to cover chapter 2 today. In chapter 2, we take a look at the chemical foundation of life. Life science, biology, is a scientific field, and biology has to follow the laws of chemistry and the laws of physics, the laws of mathematics. So all living things, we are a sum total of all chemical reactions going on in our body. Thousands of chemical reactions are currently occurring in our body right now. Every moment of our life, there is always a lot of chemical reaction going on. I give the analogy of music. If somebody plays one musical instrument well, a guitar, a banjo, whatever, if you play one musical instrument well, you are a chemist. You know, it's like chemistry, one thing at a time, one chemical reaction at a time. But you are a biologist, it's a symphony, it's an orchestra. Hundreds of these musicians are playing different instruments simultaneously, but the music is good. You know, it's melodious because they are all regulated and it's all chemical reactions working together in harmony to create beautiful life form. So biology is chemistry. In that spirit, let us review the chemistry, okay? Starting with matter. All living things, we are composed of matter. What is matter? Matter is anything that occupies some space, which means it has a volume, and what matter has a mass. It weighs something. So look around you. There is a lot of things that you see. Everything that you see around, including yourself and your pet and everybody else, is composed of matter. Now, when you break down that matter and take a closer, deeper look, you find that matters are made up of chemical elements.
You can't wear stainless. Can you wear sterling?
I'm sorry, there is some background noise here. Can you please mute your microphone? Everybody, please mute your microphone. Okay. So matter is composed of elements. Okay. Now, what are elements? Elements are pure substances. Pure substances. What are pure substances? You know, I can just give you an example. Think of gold. Think of copper, iron. Think of these pure metals. They are composed of one substance, gold atoms and gold atoms and gold atoms. Everything there is gold. So that is a pure element, okay? There are 92 naturally occurring elements, and there are more which are man-made. All these elements are organized in a table known as the periodic table. We're gonna take a look at that periodic table a little later. Now, each element has a specific chemical property and has specific physical property. Some elements are gaseous, others are solid, okay? Some are liquid, some elements are liquid in the pure form. So they have fixed chemical property and physical properties, okay? Now, elements are given their names by the scientists who discover them. The naming of the names of the element is known as the chemical symbol. Okay, chemical symbol. Let me get my, okay, chemical symbol. So for example, sulfur here, its chemical symbol is S, a single letter. In some cases, we have two letters, such as in calcium, okay? In living beings, all life forms, living organisms, we're mostly composed of a few major elements. So for example, the four most common elements in life forms are carbon, oxygen, hydrogen, and nitrogen. Now take a look at this one here. This is very interesting chart. It lists those four elements, and it lists the amount of each of these four elements present in human body. Okay, oxygen, for example, our body, 65% of our body by weight is oxygen. 18% is carbon, 10% hydrogen, 10% nitrogen. That is in human body. But if you look at the atmosphere, do you have the same kind of composition of oxygen? Atmosphere has roughly 21% oxygen, but hey, human beings, we have 65. You see, there is a disparity. There is a difference between the amount of oxygen present in atmosphere versus present in life, or the amount of oxygen present in the Earth's crust. Carbon, for example, there's hardly anything, trace amount in atmosphere and crust, but 18% in the life forms, okay? Likewise, look at the hydrogen, very little elsewhere, but a lot in the human body. What you see then is that human form, living things, they accumulate something out of the atmosphere or Earth's crust, so they accumulate and, so they maintain this kind of separation. As long as they are alive, this type of disparity, this type of asymmetry exists. Once the organism dies, then it decays and then it becomes one with nature. So the quest in life, the struggle for our survival is how to ensure that we maintain this kind of separation, we maintain this kind of organization. One way to think about this is think of very rich neighborhoods versus very poor neighborhoods, or neighborhoods that are completely obliterated. So rich neighborhoods are rich because they are sucking resources from elsewhere, and then outside can be poor, okay, poorer neighborhood. So if the poor neighborhood is, it's almost like living in nature, you being homeless kind of situation. So life is rich is what I'm trying to say in that context. Okay. Now, so we discussed a little bit our elements, chemical symbols. Now let's talk about the atoms. An atom is the smallest unit of matter, smallest unit of element that, so for example, if you take gold element, you can fragment that gold into smaller and smaller and smaller pieces. Ultimately, you come up with an atom. That gold atom has the property of gold. Okay, gold atom has the property of gold. Can you then further break down that gold atom? Yes, you can. Using nuclear reactors, you can break the gold atoms. But what do you get? You get nucleus, you get protons, you get neutrons, you get electrons. Now these protons, neutrons, and electrons are subatomic particles. These guys do not have the property of gold. So what is an atom? Atom is the smallest unit of matter that retains the property of element. You can break an atom, but then those subatomic particles lose that elemental properties. Okay, so that is the idea. Now we're going to talk a little bit about the atomic structure. I'm sure you're familiar with atomic structure from your high school or other chemistry or biology. So, atoms at the center, they have a nucleus. This nucleus is different from cells' nucleus. Eukaryotic cells have a nucleus, which is different, okay? But this is the nucleus of an atom, which contains protons and neutrons. Protons and neutrons have a molecular mass of 1. And then on the outside and the surrounding, there is a cloud of electrons spinning around those nucleus. Okay. So here is the charge. Protons have a +1 charge, positive charge. Neutrons have no charge, and electrons have -1 charge. Okay. an element or an atom in a periodic table is neutral because they have equal number of protons and equal number of electrons. So for example, carbon has 6 protons and 6 electrons. Okay. Oxygen has 8 protons and 8 electrons. So an atom by itself is neutral. When it comes to mass, the mass or the weight is measured in a unit called AMU, atomic mass unit. This is also known as Dalton. 1 Dalton. Proton is 1 Dalton, neutron is 1 Dalton, electron is 0 Dalton. It's not exactly 0. There are roughly 2,000 electrons that weigh equal to 1 neutron or 1 proton. So, 2000, already the protons and neutrons are small. When you compare them to electrons, electrons' mass is negligible. So here they write 0. It's not exactly 0 though, okay? This is a model of an atom, atomic structure. What do you see here? You have the nucleus. Inside the nucleus, these things with the plus charge, these are protons. This particular nucleus has 2 protons, and these orange looking thing, yellow orange looking thing, these are neutrons. There are 2 protons and 2 neutrons. So its molecular mass is 4 because each one of these has a mass of 1. 1, 2, 3, 4. This is helium element, helium. Now, helium has 2 electrons spinning around it in the first shell or first orbital. The first orbital has a capacity of 2 electrons. So, and then it has got 2 electrons. So basically it is full, it is happy. So this is how you represent atomic structure. This type of display, this type of atomic structure was proposed by a chemist, a scientist known as Niels Bohr, and it's also called the Bohr's model, okay? So now there are a few questions in the exam or in quiz that ask you to figure out the atomic number, atomic mass, do the calculation. It is fairly simple, okay? So I'm gonna explain that here using carbon as an example. Take a look at carbon here. This is carbon. 6 is the number of protons. Number of protons. Number of proton is its atomic number. Atomic number represents number of protons. 12 is the mass. In this case, 12 is the mass. The larger number is the mass. In this illustration here, in this diagram, 12, the mass is written on the bottom, but typically if you look at many other textbooks or other, normally they would switch it, 12 would be on top, 6 would be in the bottom, but in this case, the mass is written below like this. The larger one is the mass, smaller one is the atomic number, okay? That's how they represent. Here is another carbon. Atomic number is 6. This atomic number shows way in the periodic table, in the 6th house in the periodic table. That's where this carbon is situated. What is the difference between these 2 carbons? The first carbon has how many neutrons? Mass is 12, right? So basically 6 protons. When you add 6 neutrons, 6 plus 6 would be 12, right? But here, number of protons are 6. They do not change, but number of, the mass is 13. So what happens? It has got 7 neutrons, 7 neutrons. So this is the mass number, okay? Now, let's review about isotope, just like these 2 guys here. So they both are carbon atoms. They have carbon properties, but this one is a lighter carbon. This is a heavier carbon. This has got more neutrons compared to this one, okay? C13 has more neutrons, 1 extra neutron compared to C12. So these 2 carbons are called isotopes. Iso means same, topo is the form, same form. So here are the three isotopes of hydrogen. So the traditional normal hydrogen, also known as protium, has one proton and one electron. But now you have one extra. So this is a molecular mass of 2. So this is deuterium. This is also hydrogen, okay? This is tritium is another kind of hydrogen, okay? It has got 2 neutrons and 1 proton, 2 neutrons and 1 proton. So all these three are hydrogens, hydrogen isotopes. This is heaviest, this is heavier, this is the normal light hydrogen. Okay. Now there is a YouTube video that explains about isotope, atomic mass, etc. Please review it on your own time. Yeah. Now those isotopes, especially the carbon isotope, is used in a technique called radiometric dating. This technique allows you to figure out the age of the specimen here. So here is some fossil, some bones that are buried. When people discover these kind of bones, the first question you want to know is how old is this thing? How old is this thing? And what they do is they scrape some tissue or some bones and they figure out how much C14, carbon 14, which is heavy carbon isotope, is present in the bone. Now, the heavy carbon C14 has a constant rate of decay. If you start with 100 grams of C14 now, 6,000 years later, after 6,000, there is only 14 grams. So it just decays over time at a constant rate. So the people who are alive here, they have certain ratio, certain proportion of C14 in our body, okay? But this bone here has a smaller amount of C14 compared to the normal carbon. So by calculating the ratio of C14 present, because that ratio of C14 will diminish over time, will decline over time, you know, as the fossil, as the bones age, okay, it'll decline. So that then is used to calculate the age of these bones. Now this technique, radiometric isotope or radiometric dating using carbon, can date or can figure out the age of these bones if they are roughly 50 to 60,000 years old. If something is older than 60,000 years, carbon dating does not work because nearly all of that carbon 14 would have been disintegrated, would have been gone. So you would not know how old the structure is. You have to use some different type of isotope that has a longer half-life, okay? So here is an example of periodic table. This periodic table lists 103 elements. Of these 103 elements, only 92 elements up to uranium here, they are naturally occurring elements. The rest of them are man-made in a nuclear reactor. Now, the periodic table has these rows, these columns here like that. This is a column 1, 2, 3, 4, 5, etc. 18 columns. These are called the groups. So, you know, you see 18 groups here. And these rows here like this, they are called the periods, okay? Group go vertically, periods go horizontally, okay? Each element has a location, a position in the periodic table. So for example, iron's atomic number is 26. That means it has got 26 protons. Its atomic mass is 55. Now you can calculate 55 minus 26. That is how many neutrons it has got. Notice that sometimes you have these neutrons in decimals, which means, you know, they are just averaging all different kinds of isotopes. So, you know, you do not have a just round number here, okay, round number. All the elements that are in group 1 share similar chemical properties. Those in the group 2 also have similar properties. This group 18 here, they are called noble gases because their outermost shell of electrons are filled. Okay, they are noble gases. So anyway, the chemical properties of the elements are similar if they fall in the same group. Okay. This is the electron model. This is called the Bohr's model, where you have the nucleus and then you got various shells, orbitals, where the electrons spin around, okay? This is Bohr's model. Now, this is an older model. There are more, recent models, quantum models that show accurately how the actual atoms look like. But for our purpose, we can just stick to this Bohr's model because, other things you will be studying in chemistry anyway, in advanced courses. Any question about this so far? So far, are you okay? Let me get some water. Okay. So now in this diagram, it only is taking a few chemical elements. They belong in different groups and different periods, okay? They are representative elements. Just to show you this concept, when two atoms come together to combine to form molecules, they meet each other by the outermost electron shells. So the communication between the two, the interaction between the two atoms happens at the electron shell level. The nucleus itself is buried deep inside and it's not coming in contact with another nucleus. It's the electron cloud that interact with each other. And which electron cloud? The one that is in the outermost shell. Outermost shell. Here they are indicated by this red line, okay, red line. Now, with the exception of the first shell that has a capacity of 2 electrons, these guys are filled, so 2 electrons, helium is full. Hydrogen here has only 1 electron, and there is a vacancy of 1. 1 electron is, is not present. Think of this shell like an apartment. An apartment at least needs to have 2 people. Only 1 is here. It's looking for a partner. The partner is not available. There is a vacancy of 1. This one, oh, they are occupied. They both are here. They are happy. So this vacancy in chemistry, they call valency. Okay, so it has got a valency. It has got a shortage of 1. Now take a look at these various representative elements in the second period. Lithium, for example, on its outermost shell has only 1 electron, okay? The subsequent shells, they have a capacity of 8 electrons, okay? You need to have 8, just like this guy, to be happy. This guy has 2, 2, 2, 2, 4 apartments, and you have got 8 different electrons, 8 electrons. So this is happy. Is this guy happy? It has got 1. Now it has to have 7 more electrons. That is going to be a tough order. Look at carbon here. Carbon has a valency of 4. There are 1, 2, 3, 4 electrons. Each one has a vacancy of 1. Fluorine, it's almost full with the exception of this guy here. This needs a partner. Okay, that is fluorine. Neon is full. So the strategy that elements take to fill the valency is that if you are closer here, so for example, fluorine, it will gain that extra electron. It's hungry and it will pull the electron. if you are in this period one, it's easier for you to lose this electron and be happy with the remaining two. So some of these guys will donate the electrons. These guys will accept the electrons in order to maintain a saturated valence shell, okay? So that is a valence shell. Okay, so this is electron. So in quantum mechanics, the electron shells, they are not really round orbitals like these, but they are more like that. Okay, Bohr's model is somewhat dated, so please review this animation here that explains how those electron shells are configured, in this element, scandium. Okay, there's somebody who says, oh, they got into the campus and they parked. Okay. So I guess the traffic is bad, so people are trying. Maybe some of you are listening in your car, but okay. Like I said before, electrons determine how the atoms react, okay? So now let's talk about the molecules. Atoms interact with other atoms in order to fulfill their outermost shell, okay? To share or to donate the electrons, somehow they want to maintain their outer shell filled. In order to attain that state, atoms participate in various chemical reactions, okay? Now, a chemical reaction is shown like this. On the left-hand side, you write down what are called the reactants. In this case, this is hydrogen peroxide. You can buy hydrogen peroxide. It comes in brown bottles. When there is a cut or some kind of injury, you put a few drops and you see that little fizz coming out. That fizz is the result of this oxygen, O2, oxygen is coming out. So hydrogen peroxide breaks down to water and oxygen. Now, if you count the number of hydrogen here on the left-hand side, the reactant side, and the number of hydrogens on the right-hand side, it is same. 2 times 2 is 4, 2 times 2 is 4. If you count the number of oxygen on both sides, it is the same. What is the difference between the two is the rearrangement. Those atoms here in hydrogen peroxide are grouped differently. It used to be one molecule, but now there are two molecules. So this is the product. This is the reactant. Reactant is the starting material. Product is the end after the reaction has been done. And those reactions are shown by an arrow. In this case, this is a solid one-way arrow. Most chemical reactions are like this, where these reactions are reversible. The one that I showed, hydrogen peroxide, is an irreversible reaction, meaning it just goes one way. And these things, water and oxygen, do not combine and reform hydrogen peroxide, okay? But here you have carbonic acid. This carbonic acid, if there is a lot of carbonic acid, then this will dissociate to form bicarbonate and hydrogen ion or proton. This is hydrogen ion proton. But if this is in excess, if there are a lot of protons, then this reaction will veer towards that. It's almost like a pendulum. If one side is too much, it tends to flow into the other direction. If the other side is too much, it tends to flow backwards. So this is going to be a reversible type of reaction. Most reversible reaction, in real situation, reach an equilibrium. Equilibrium is where the two sides are balanced. If the other side goes high, it tends to go to the left, And if the left is high, it tends to go to the right. Think of the pendulum. Now, a chemical bond is the link that connects the two atoms. And we are going to consider different kinds of chemical bonds next. The first one is the covalent bond. Okay, covalent bond. Covalent bonds result from sharing of electrons, sharing of electrons. Let me give you the example of water, okay? Water has oxygen. There are 6 electrons on the outer shell of oxygen, 6 electrons. These 2 are happy, they got partner. This apartment is filled, they got 2. But look, this guy is empty, alone. This guy is empty, alone. So this needs a partner, this needs a partner in order for oxygen to be content, to be happy, okay? To have octet state. Octet is the happy state. Now you have hydrogen. Hydrogen has 1 electron on its outer shell. So this 1 electron wants to maintain 2. This hydrogen wants to maintain 2. So now they come together and join, they share the electrons. So the oxygen thing includes the hydrogen's electrons in its count. So oxygen thinks it has got 8, oxygen is happy. Hydrogen thinks that it has got 2, and hydrogen is also happy. But now they are kind of permanently linked. And as a result, I do not know whether you can see it here. Let me just show if you can see this one. See this one here, water. Okay, the white one, the white little balls are, they represent hydrogen. The white one represents hydrogen. The red one here, okay, that represents oxygen, okay, hydrogen and oxygen. Now, they are sharing electrons, so it's very difficult to pull these two guys apart. So the link, the bond, how tightly they are linked, you know, the glue is the bond. Bond, you know, it's like, you know, we are bonded to our children, meaning that we have a link, yeah? So this is hydrogen and oxygen are linked. So that is a covalent electron sharing bond, okay? Now these electron sharing bonds, they come in 2 flavors. In water, this electron sharing is not fair. This electron sharing is not even. In fact, the oxygen has a greater pull for electrons. Oxygen is very hungry for electrons. So basically, you know, it says to hydrogen, hey, let's share the electrons. But guess what? Oxygen is getting most of the electrons anyway. Hydrogen thinks that it is sharing, but only occasionally those electrons come around it. So, you know, it's kind of half naked, hydrogen. Whereas oxygen is getting the electrons most of the time. When that happens, this covalent bond here develops what we call polarity, meaning the hydrogen side becomes slightly positively charged, hydrogen end becomes slightly positive. Oh no, so I have to draw it like this, yes, so. Slightly, hydrogen end becomes slightly positive, whereas the oxygen end becomes slightly negative, okay? So this is a covalent bond. That covalent bond has, you know, this covalent bond, this end, hydrogen end is positive, oxygen end is negative slightly because of the way they share the electrons unfairly, okay? Okay, let me erase that guy. Now, here is a electron sharing between 2 oxygen atoms, okay? This oxygen, this electron and that electron, this electron and that electron, they are shared. So, you know, we give 2 double bonds here, 2 lines. Each line represents 2 electrons, okay? It's electron sharing. That line represents electron sharing. But in this case, there is equal pull. In the pull for electrons, in that tug of war, they both are equal. And therefore, there is no polarity. Okay, so these will develop into non-polar covalent bond. Whereas in water, this is developing into polar covalent bond, okay? So you will be asked questions about polar and non-polar covalent bonds, in some questions, yeah? Now, the other type of chemical bond is called the ionic bonds. Ionic bonds are the result of electrical attraction, development of charge, and oppositely charged things are attracted to each other. So take a look at salt here. Salt is made up of a molecule made from sodium and chlorine. Sodium on its outermost shell has one electron, which it is happy to give away so that it retains the remaining octet state. When sodium gives away its electron, the sodium side becomes positive, fully positive. Now, chlorine, on the other hand, has 7 electrons on its outer shell. It just needs 1. And it's very, very happy and eager to take that 1 electron from sodium. But when chlorine receives that electron, it becomes negatively charged. So now sodium side becomes plus charge, chlorine side becomes minus charge because it has acquired that extra electrons from sodium. Now these charged atoms are called ions, okay? And therefore the bond, the attraction between these two guys, the negative attracts positive, and that is called the ionic bond, okay? Now ions may be positive. They are called cations. Think of cations, or negative, anions. Negative charge is anions, positive charge is cations, okay? So here is the summary. Polar covalent bond, the attraction between these opposite charges. This is a covalent bond, but there is a little charge here. Now this is a non-polar covalent bond, okay? So there is no net charge here, okay? So this talks about the polar and the non-polar charges, okay? Polar and non-polar covalent bonds. Okay, so now let us talk about the third kind of bond, which is the hydrogen bond. Hydrogen bonds are the weak interactions. So let me show you this example here, a hydrogen bond. You see this water molecule, right? These two, hydrogen and white, has slight positive charge. The oxygen has slight negative charge. But if I take a cup of water and look at the water molecules inside, okay? So they're gonna be like this. Look at this one here. So a water is sticking to water, okay? Water molecule is sticking to water. You notice that? And you also notice that the white, which is hydrogen, is sticking to the oxygen end, so negative, positive. So once again, in this example, these two bonds, oxygen and hydrogen within a water molecule, this attraction is covalent, polar covalent. But between this water molecule and the other water molecule, between the water molecules here, so that bond, this link here, this link between this one water to the next water, that is hydrogen bond. That is electrical attraction. It's a weak electrical attraction. So water has hydrogen bonds because the water molecule is polar, okay? We're gonna talk more about the water and its chemistry in a minute now, okay? The last one is van der Waals interactions. This is a very, very weak interaction that results from the very rapid spinning of electrons. When those electrons are spinning rapidly, sometimes they veer a little bit too far on one direction. And the opposite side becomes slightly positively charged. The side where electrons are present uh, go momentarily, that becomes negatively charged. And there is a flickering, slight negative positive charge that builds in a group of molecules, which results in somewhat, interaction between those, attraction between the molecules, because there's always constant uh, slight charge that develops. As the electrons are spinning very, very fast, they veer off one direction, and as a result, create slight negative or positive charge. Okay. We have questions, guys. I'm going to switch now. This simple review of chemical bonds. Uh, okay, I'm also reviewing this chat window here. Seems like there are no questions. So far we discussed atoms, mass, elements, atomic model, ions. So that was, some basic chemistry, yeah. And chemical bonds. In chemical bonds, we discuss ionic bond, covalent bond, polar, non-polar covalent bond, hydrogen bonds, and then van der Waals interactions. The next idea, or next thing that you need to learn is the properties of water. Why water? Water is essential for life. Roughly 70% of our mass, our weight, is due to water. So there's a lot of water. All life's chemistry happens in watery solution, watery environment. Therefore, it is important for us to understand the chemical properties of water, okay? Water is, like I showed you before, water is made up of hydrogen and oxygen. It's a very simple molecule. It's a polar molecule. But that polarity causes a lot of wonderful emergent properties which help water foster, support life, okay? So here are hydrogen bonds. These dashed lines show hydrogen bonds. Hydrogen bonds are due to the polar covalent bond. This covalent bond is polar. Why? Because hydrogen end is slightly positive, oxygen end is slightly negative. They are shown by delta positive and delta negative here. And a cup of water, a drop of water has, many trillions of water molecules interconnected by the hydrogen bonds. Do you see covalent bond here? Yes, this black solid line is the covalent bond. This dashed line is the hydrogen bond, okay? So water can exist in 3 different states. We are familiar with liquid water that we drink, gaseous water, water vapor in the atmosphere, relative humidity, etc. There's a lot of water in the air. So this is a gaseous water, water vapor. And there is solid water, which is ice. When you cool water, it becomes solid. So water exists in these 3 different states, okay? Here is an example of ice. Ice results because the molecular motion slows down. So let's say in liquid water, all these water molecules here, they are kind of constantly moving. The hydrogen bonds are breaking and reforming, breaking and reforming, okay? But when it becomes solid water, the mobility becomes small, and these guys organize like this. You see here, so they are organized like that, like that. So here is a hole, here is a hole. So basically, it increases, expands the volume, so all these holes here, these holes, because the hydrogen bonds become steady, and then, these water molecules will tend to occupy a larger space. So earlier I used to fit this in a cup, but now when I add it, you see, water molecule expands. Try putting a bottle, plastic bottle full of water in a freezer and see what happens. That plastic bottle will rupture, will break, yeah, because ice expands, increases the volume. As a result, it is less dense, and as a result, it floats. This is remarkably wonderful for living things, because imagine if all these ice were to sink, if it were to sink, the oceans would freeze bottom up. So all the living things inside that water would die. Instead, what really happens in nature is ice will float, and under the sheet of ice, there is liquid water that can sustain life for a long term. So this is wonderful property of water. Water has what we call a tremendous high heat capacity. It is the amount of heat that water can absorb. When you boil water, the boiling water has a temperature of 100 degrees, and it remains 100 degrees until all that water has evaporated. It has got high heat capacity. It just does not easily cool, or it just does not easily heat up. It can absorb a lot of heat, okay? Heat of vaporization is high, like I said. So, and then water is what is called the universal solvent. Now, if you put a spoonful of salt in water and stir, where does the salt go? It just dissolves completely into the water, right? It dissolves completely. So the final salty water, the water tastes salty. There is salt inside, but you cannot see the salt, right? So this salty water is a solution. Water itself is the dissolving agent called a solvent, and the salt is called solute because it gets dissolved into water. So think of sugar water. Now you add sugar, a spoon of sugar in a cup of water and stir, sugar disappears. The sweet water is solution. The sweet water is solution. Water itself is solvent, and sugar would be the solute. Okay, so you got to know which is which. So in any given solution, you got to figure out how much of that solute is present. You do not see them, right? So it can be very, very salty. It can be mildly salty, or it can be just small pinch of salt, right? So the amount of salt molecules vary. So chemists want to know how much of that salt is or sugar is present, okay? And that measure is called the molarity. So, so I'm just gonna explain what that molarity is, okay? So 1 mole of a substance is its gram molecular weight, okay? 1 mole has Avogadro's number of molecules, which is an astronomically large number. So here is an example for salt. Sodium has a mass of 23. Chlorine has a mass of 35.5. So when you add the two together, 58.4 or 58.5 is the mass of salt, 1 salt molecule. So what you do is you take 58 grams of salt and put it in, and make 1 liter solution, 1 liter solution. That is called 1 molar solution. Okay, 1 molar solution. And 1 molar solution will have these many molecules of salt, these many molecules, Avogadro's number of molecules. Okay. So here is an example. How would you make half a molar solution? Okay, it's a question. If you dissolve 58.44 gram in 1 liter, make 1 liter solution, then it becomes 1 molar. If you want to make half molar, don't take 58.44, divide this by 2, so 29.22 grams of salt in 1 liter of water, and then you get 0.5 molar solution, okay? Now, water can form hydrogen bonds with other polar molecules. So this is how water dissolves other things. So for example, chloride ion here, chloride ion, it's a negatively charged ion. This is an anion because it is negatively charged. The hydrogen end of water, which has a positive charge, gets attracted to this negative charge. And this is how, it just dissolves the chloride and the sodium here. The oxygen end is attracted to, the sodium. Okay. Now, another emergent property of water is cohesion. Cohesion is water sticking to water molecule. Look at this drop here. This drop is, all the water molecules in these drops are clinging to each other, hanging to each other by that hydrogen bond. Okay, so that is the cohesion. Now, there is adhesion. Adhesion is water sticking to your cloth, water sticking to any other surface. Water makes whatever surface wet, that means water is sticking to that other stuff. That is adhesion. And surface tension is the property of water which combines both cohesion and adhesion, okay? So take a look at this example. Here is a glass capillary. This is water. So water sticks to the side of the glass and water sticks to water. As a result, you have this kind of sagging, okay? And water can rise up to this little capillary. This is called capillary action, capillary action. This is important for uptake of water by plants. Okay, and you see surface tension, example of surface tension here. So this bug is walking on water without really breaking the surface of the water. Okay. Question, guys? Okay, so what I want you guys to do is wait for 4 minutes here. I have to take a little pause here. I got to take a restroom break. Sorry, and then I'll come back, okay? Okay, welcome back, guys. Sorry about that. I was hoping that there will be a bunch of questions here in my chat window. Looks like you guys did not have those questions. Okay. So now I'm going to cover another important aspect of water, which is ionization of water. Okay, ionization of water. And this covers the topics such as acids, bases, pH, and buffer. This is sometimes people find it hard, but this is a simple concept, which is really the property of water, right? So think about water, okay? Liquid water here, I have let me see. So this is liquid water. And liquid water, in a liquid water state, all these hydrogen bonds are breaking and remaking, breaking and remaking like that. Yeah, so liquid water goes like that. Occasionally what happens is that liquid water, the hydrogen and oxygen that are linked by covalent bond, occasionally one of the hydrogen gets detached. When that happens, water molecule breaks like this. You see, this is just a hydrogen ion or a proton alone, okay? And now what do you have? You have, look at this one here, OH group, oxygen and one hydrogen. The other hydrogen here is missing. So this is called ionization. Water is splitting. So take a look here. So H2O liquid, in aqueous solution, occasionally, not all molecules, okay, a few molecules out of many, they dissociate like this. They break apart like that. This is called ionization of water, okay? In pure water, these many molecules, 10 to the power -7 moles in a liter, are ionized. So there's always going to be a small population of molecules that are ionized, okay? Now in liquid water, what do you think will happen to this hydrogen ion, this proton? It is in liquid water, right? What happens is that, this is not going to stay alone like this. Okay, you see this one? This is not going to stay alone like this. What happens is that it'll create a molecule. That hydrogen ion proton will link to another oxygen that has a negative charge. So this is called H3O or hydronium ion, okay? Hydronium ion. People use this synonymously. The hydrogen ion, of course, this is the result of dissociation of water, but when you are in a watery environment, this guy cannot stay by itself. It quickly associates with water and it becomes H3O. So when somebody says hydrogen ion or hydronium ion, it's the same thing, okay? Is that part clear? Once that is clear, the rest of it is very, very easy, okay? Again, water breaks down to hydrogen ion or proton and hydroxide ion. Aqueous solution, okay? This is aqueous solution. So now, what is an acid? An acid is a substance that floods or adds hydrogen ion in the solution. So it increases the amount of hydrogen ion in the solution. That is an acid. Typically, acids taste sour. They are sour in taste, hydrogen ion. Now, the opposite is a base. Bases will remove hydrogen ions, increase the hydroxide ion concentration, increase the hydroxide ion concentration. Because if you have more of the hydroxide ion, they combine to hydrogen, they take it away and convert to water. So acids and bases are just the opposite. Acids increase hydrogen ion concentration. Bases will have less hydrogen ion concentration. Okay, that's the acid and base. Now, what is pH? pH is simply a ruler, a measure that pH is a ruler or a measure that indicates how acidic or basic the thing is. It's a measure of acidity or alkalinity. And what are buffers? Buffers are special kind of chemicals that behave as acids if there is too much, if there is too much hydroxide ion, then they act as acids. And then if there is too much hydrogen ion proton, they act as base. So basically they take the counter position in order to maintain the pH balance, okay? In order to maintain the pH balance, buffers take the opposite position. Too much hydrogen ion, they lower it. Too little hydrogen ion, they dump it, okay? That is nature of the buffers. For example, in our blood pH level has to stay constant. So we have chemical buffers that will ensure that our pH blood pH level is staying put, it's staying level, okay? So here is a pH scale. pH scale ranges from 0 to 14. All these numbers are 10 to the power, 10 to the power 0, 10 to the power 1, 10 to the power 2, etc., etc. So basically what is, it's a negative number, 10 to the power negative 2. So what that means is that when you have 0, it has got a lot of hydrogen ion concentration, 10 times less hydrogen ion concentration. So when you have 14, hydrogen ion concentration is really low. Sometimes people have the, it's difficult to conceptualize because, the number 14 obviously is large. How are you saying hydrogen ion is low when the number is actually large, right? It has to do with how the pH scale is defined. So here is this bold line. pH is the negative base 10 logarithm of hydrogen ion concentration. So for example, if you have 10 to the power negative 7 hydrogen ion concentration, the pH is going to be 7, okay? So here is an example of buffer, carbonic acid here, it can dissociate this way. It's adding the hydrogen ion concentration, it's dissociating that way, it's removing the hydrogen ion concentration. As a result, this can act as a buffer. So here is an implication, ecosystem implication of the hydrogen ion concentration, ocean acidity, etc. right? So take a look here. This airplane is dumping a lot of carbon dioxide. The level of carbon dioxide in our atmosphere is rising. So if there is a lot of carbon dioxide in the atmosphere, in water, this is the ocean, the carbon dioxide reacts with water to form carbonic acid, which then dissociates to release hydrogen ion, the protons, okay? Now, these protons react with carbonate to make bicarbonate, okay? So if there is a lot of carbon dioxide, you end up making a lot of this carbonate into bicarbonates. But guess what? These carbonates are needed, carbonate forms are needed to combine with calcium to make this shell. Calcium carbonate is the shell, like eggshell, coral shells, etc. For the corals, they need to make this calcium carbonate, okay? So if you take away this carbonate, then the calcium carbonate cannot form. This carbonate is being siphoned away by the hydrogen protons, these hydrogen protons coming from, excess CO2 in the atmosphere. When this happens, then the ocean ecosystem, the coral health will diminish over time. And then, it affects the biodiversity, it affects the fish population. Ultimately, it is really harmful for human health. Okay, so now in the next 5 minutes, I'm gonna talk about the carbon compounds. You guys have any question? If you have any question, please unmute your microphone. If not, let's review quickly the carbon compound. Now, our body's chemicals are in a watery environment, but our proteins, carbohydrates, etc., they are made up of organic chemicals. Chemicals, that are carbon-based. Now, carbon is unique because it forms 4 bonds. It's smack in the middle. There are 4 electrons. It cannot give away those 4 electrons. It cannot donate. So what it needs to do is, it has to share those electrons. So it is really wonderful in sharing the electrons. So electron sharing happens, for example, this is methane. This black dot here represents carbon. Hydrogen, 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 4 hydrogen carbons. So this is a hydrocarbon. This is a hydrocarbon. Okay, and this is covalent bond. These covalent bond is not polar. This is a non-polar covalent bond because electron sharing is fair here. Okay, so now carbon can also form a covalent bond with another carbon. Carbon can form single bond, it can form double bond, so double bond means this guy, this carbon has 2 electrons, that carbon shares 2 electrons. So each line here represents 2 electrons, okay? So this is electron sharing bonds. Carbon can also form this kind of circle chains. If you notice, there are 4 lines coming out of each carbon. So carbon has a valency of 4. It's sharing 4 electrons, some with carbon itself, others with hydrogen. Sometimes double bonds here, okay? So now carbon can form a variety of chemical compounds. Okay, take a look at these chemical compounds here. So this is, these are called isomers. Here is butane. It has got 1, 2, 3, 4 carbons, and 10 hydrogens here. 4 carbons and 10 hydrogens. But it is in a sequential order like that, yeah? But here, the same thing, isobutane, but the way they are organized are different. So these two are different chemical compounds. These chemical compounds are called isomers. Please do not confuse isomers for isotopes. Isotopes are heavy atoms. Isomers are, chemicals that have different structures, where the atoms are organized in a different manner. So these are structural isomers. Here is a case of geometric isomers, and here is a case of enantiomers. So now take a look at this one here. So I got a double bond between the 2 carbons, and really these are chlorine, these are hydrogens. So now what is happening is, so you can have a situation like this. You can have a situation like this where, these 2 chlorines are in opposite direction, opposite plane of this double bond. Whenever there is a double bond, this molecule does not rotate. If there is a single bond, let me just show you a single bond here. If there is a single bond here, these guys can rotate in its axis like this, yeah? Rotate like that, single bond. Double bond, it's fixed. So when the double bonds are fixed, if you have groups that are attached in the opposite side, this is called transorientation. So that is one molecule, one chemical. It has got one property. But take a look at another property, the cis side. Cis side is, the 2 things are in the same orientation. So this is cis configuration. Cis configuration. You see these 2 guys are in the same side, cis. If this was on the opposite side here, that would be trans. So they are different molecules. They are geometric isomers. Enantiomers are mirror images. So, you cannot superimpose one with the other. They are like your hands, so it's like my hands, I cannot superimpose. You cannot put the left glove on a right hand. So those are enantiomers. Okay. So here is a hydrocarbon. These are different kind of fatty acids, so one is a saturated fatty acid. This is unsaturated fatty acid. Finally, this one is the big one, yeah? This one is the big one. Please take a close look at these functional groups. It lists many different kinds of functional groups. There is another worksheet in the study area, so please take a look at those 2, okay? These functional groups are little attachments on large molecules that will completely change the property of that molecule. So, you have the carbonyl group, hydroxyl group, amino group, phosphate group, etc. They confer different properties to these chemicals. So for example, I have this OH group. OH group. Whenever you have this OH group, it makes the thing alcohol, okay? So this is, OH group will make, alcohol, hydroxyl group, OH, okay? So there are some examples. I am just gonna show you, hopefully I have. Oh, never mind. I think we are almost running out of this time. So what I'm gonna do is stop it here, stop my recording. Okay.